Excellent. So thank you, Laura, for the kind introduction, and thank you, Andre, and the organizers of CPP for the invitation. It's a pleasure for me to be part of CPP this year. I was originally planning to be in person at the conference. However, we at the family, we were one by one getting COVID. So at the end, I decided it was safer not to go and to present virtually. So as Laura mentioned, I moved to Amazon Web Services last year in June, and I'm currently leading the simple storage service at Automated Reasoning Group at AWS. But before that, I spent 20 years working at NASA Langley. So this presentation is mainly a reflection on the work that I was involved during my tenure at Langley. So NASA Langley, the domain we were working on is mainly safety critical applications for aviation. We did a little bit of space, but I'm not going to talk about that. I'm going to focus on some of the applications, but more than the applications, I'm going to focus on the work on theorem proving that we did during these 20 years, and that they continue to do. I mean, it's not that they stopped working on theorem proving. And as a matter of fact, Laura presented a paper in this conference yesterday on the work that they are currently doing. So let me start from the very beginning. And this was the first project that I participated at Langley. It was in 1999, and we were asked to verify an algorithm, an alerting algorithm for parallel landing. The algorithm was implemented in Fortran, and I remember they came to me with a listing in Fortran, and the task was to verify some properties for that particular algorithm. And just to give you a context of how this algorithm works, so in the US and in the world, there are, especially in major airports, there are parallel runways closely separated, and those parallel runways can be used simultaneously, so you can have two aircraft landing in parallel. So there is, NASA was investigating at the time an algorithm for alerting pilots of a possible threat when another aircraft was landing in a parallel runway. So there are two aircraft, the on-chip that is assumed to be flying a straight line, and there is the intruder aircraft. And the algorithm works more or less as follows. Every second, you get the position and velocity of the on-chip and the intruder. And then the on-chip is projected to fly a straight line, and the algorithm is going to check a fan of trajectories for the intruder. Around the on-chip, there is a protected area. If I remember correctly, it's like 1,000 feet for this parallel landing. And then if one of these fan of trajectories that are projected for the intruder intersects the protected area, then an alert is issued. So what are the fan of trajectories that are considered for the intruder? In the algorithm, straight line trajectories and trajectories that are tangent to a circular arc path at a given constant bank angle. So the question that is asked about this algorithm is, assuming some dynamics for the aircraft, like constant speed. So what is how close in time and how close in distance the two aircraft can be before a warning is issued? And a couple of things about that. I mean, I presented this, the algorithm, very briefly in this chart. But in order to prove this property, we have to consider possible trajectories for the aircraft, in particular for the intruder. and then check if for those possible trajectories for the intruder and for the on-chip, the algorithm is going to issue an alert. This is, as I said before, the algorithm was provided to us in Fortran, and we had to write a specification of the algorithm, and then we use PBS. Langley is a heavy user of PBS, and this is the specification of the algorithm. So a couple of things about this algorithm. As you can see, I mean, it's not that complicated, but this is not completely trivial. I mean, there are trigonometric functions, and there is a loop there that I am not specifying, and it can be found in the paper. But this loop, the last line in this algorithm, the arc loop, is actually the part of the algorithm that is going to generate these trajectories for the intruder, and is going to check if those trajectories intersect the protected area of the aircraft. And the algorithm returns a Boolean. The I is the trajectory of the intruder, or the on-chip, and the E is the evader, is the other aircraft, and the Boolean that it returns is true if there is an issue, if there is an alert, of course, if the alert is not issued. So that was the algorithm. And this is the verification that we did on formally verify in PBS. So what we found is that the aircraft can be as close as 10 seconds before an alert is issued. So this is the formal theorem that we prove, is that for a look ahead time between 9.5 and 10 seconds, so between 9.5 and 10 seconds, if there is a conflict in 9.5 or 10 seconds between the aircraft, then it's guaranteed that this algorithm is going to issue an alert. And the left-hand side of this implication is everything about continuous mathematics. Is everything about trajectories. It is not the algorithm. I mean, this is considering on-chip trajectories and intruder trajectories that are continuous functions. The right-hand side of this implication is about the algorithm. So if there are trajectories that lead to a conflict, then an alert is going to be issued. So this is a positive verification that we found that the look-ahead time for issuing an alert is 10 seconds. However, the algorithm originally was designed to have a look-ahead time of 15 seconds. So it was kind of disappointed, the designers of the algorithm, that they didn't achieve that particular look-ahead time. And it's very important because the meaning of this time is that is the time that the pilot has to solve a conflict in a parallel landing. So 15 seconds is a lot better than 10 seconds, but 10 is better than 2. So it's not that bad. So the other thing about this algorithm is that we found that 10 is very close to the maximum time that you can achieve. In fact, we found a counterexample for 10.5 seconds, meaning that there are trajectories that don't issue an alert in 10.5 seconds. And at this time, the aircraft can be as close as 0.5 kilometers. And that property was also verified in PBS, but the way that we found that counterexample was by simulating in Java, in particular, the algorithm and some of the trajectories. So what is an aircraft trajectory? Of course, in order to prove this theorem, we have to assume particular trajectories for the aircraft. So for the on-chip, as I said before, we are assuming that the on-chip is flying a constant speed, straight line trajectory, no maneuvering. So the only aircraft that is maneuvering is the intruder aircraft. And the trajectories that are considered for the intruder are represented as differential functions with some constraints based on the bank angle of 45 degrees. That is the maximum bank angle that a commercial aircraft can implement. So essentially, this theorem is proven for an infinite number of trajectories for the intruder. And as I say before, I mean, those trajectories are continuous functions with some constraints on the turn radius for the aircraft. This verification is one of the most involved verification that I participated during my tenure at Langley. It is still very, very involved, complex. We spend a lot of time proving those properties, finding the right way to formalize the dynamics of the aircraft, for example. And you can read about them in the reference that I provided here. But by the way, there are several references in my presentation. It's not self-service. I really want to acknowledge the contribution of the many people that participated in this work. In any case, the verification the verification of this algorithm was a good point a turning point at NASA Langley in the sense that it provided a direction for future verifications in this area. It opened a whole area of a whole domain for us at NASA Langley. After this verification of AILs, we started working on more other type of algorithm like conflict detection and resolution for commercial aircraft, and then we move into autonomous aircraft. So it opens a whole area of research in theorem proving, but it also provides a direction on what we needed in terms of theorem proving for these kind of systems. And this is more or less the direction that it provides, but it's also the overview of my talk. So I'm going to talk about some of the lessons learned in AILs and how they evolve in 20 years. So the first lesson was about hybrid verification. And by hybrid, I mean many things. So one of the first concern that we have when we started doing the verification of AIL is how foundational we wanted that verification to be. And this was, as I said before, we started working on this in 1999 when there were not many libraries in PBS. So we had some initial libraries for analysis, but we didn't have, for example, a very good trigonometric library in PBS. So that was a big decision because we wanted to make progress on the verification, and so we decided at the very beginning that some of the traditional or well-known axioms for trigonometric functions, we are going to assume them, and we are not going to prove them. I mean, those are going to be uninterpreted functions, so that we can use them in other proof, but we are not going to spend too much time working on those axioms. So we have a whole library, a whole axiomatic library of trigonometric functions, and this is one of the simple ones, but we also needed a tangent and arctangent and many other things. But not all the axioms that we introduced in that specifications were that foundational. As an example, I provide here an axiom 2 that was also provided as an axiom. So we didn't have a formal proof of that. But we needed in some of the proof. At that time, there were not sophisticated SMT solvers, in particular for nonlinear arithmetic. So we use computer algebra tools, and in particular, I use MuPath, computer algebra system, to check some of these axioms. And when I say to check, I mean, it doesn't. I don't necessarily mean that we prove those axioms in MuPath, but we use MuPath in order to graph these particular functions and visually check that these properties were satisfied. So it was a very manual process, but we wanted to make progress, and we did. And there is a handful of actions. I mean, there is one theory with all the actions that we use. There are, like, if I remember, like 5 axioms of this kind, but the rest of the file, the rest of the element was really theorem proving. So that is one aspect of the hybrid approach. Like, the other aspect is that we at the beginning, when we started working on the verification of AILs, we tried to discretize everything, the trajectories of the aircraft, and try to follow a more discrete approach. But we soon realized that we needed, for the kind of property that we were proving based on times and distances, we needed a more precise model. And then we decided at that point that we needed continuous behavior, and that everything that was based, everything related to the aircraft dynamics, it would be easier to specify as continuous behavior, as continuous dynamics, and of course the logic is going to be discrete. And then the other aspect of hybrid is that we started to mix trusted and untrusted systems in our verification. So we trust PBS, we don't trust MuPath, but we needed these untrusted oracles in order to make progress, and we decided to do that. However, it was clear that we needed to integrate, as SMT solvers were evolving, it was necessary to integrate them into PBS. So this manual labor of working with computer algebra tools and visually checking, I mean, that is maybe good for the first time, but we needed something better than that. So we started working on integrating external tools into PBS, even though they are still oracles. However, there is less chance for errors because the whole integration is automatic. And then we integrated, and it was really a very good step in the right direction. We integrated Metitarsky, that is a theorem prover, an automated theorem prover for real value functions, into PBS, and we integrated Metitarsky in a very idiosyncratic way. So in particular, this sequence that I'm presenting here is an actual sequence of an actual verification that we did after AILs. Is the verification of a concretation resolution algorithm. This particular sequence has like 13 variables, if I remember correctly, and is automatically solved by Metitarsky. And the other aspect, when I say idiosyncratic, I mean it's when we integrated SMT solvers, we decided that this particular SMT solver or automated theorem prover, we decided we needed the integration at the level where the user, at the level of the user. For example, it's never the case that we have a very elegant formula of the form for all x, there is a y such that this and this and that. Is almost never the case that those formulas are that nice. I mean, the formulas are with sequence, and some of these some of the formulas in the sequence had nothing to do with the actual property that we are trying to prove. And this sequence, I mean, they don't necessarily have variables per se, but they may have, but real variables. I mean, they may have variables of record, and one of the elements of the record is a real number. So all these details are integrated are taken into account into the integration in Metitarski, so that we get rid of formulas that have nothing to do with real numbers, and we generalize and introduce real variables when we need them. And to finish my story with this sequence, this particular sequence appears in a branch where there are like 100 other sequences like this one. So at some point in the verification, where we have to split in many cases, and all the cases are like that. So it is what we have is a strategy that we have to call 100 times, and is automatically solved all these 100 cases. So it was a very successful integration, and we use Metit in almost all the verification that we do. I mean, we are not ashamed of using untrusted oracles, and this has been a very useful integration into PBS. I say untrusted, but untrusted from the point of view of the logic of PBS. I mean, I know that automated theorem provers, they are working on, and in particular in the case of Metitarski, working on generating proof certificates, and if those proof certificates are generated, maybe we can have a trusted integration with PBS at some point. So that was that was the first lesson. It was to do a hybrid approach and to mix untrusted and untrusted oracles. The second one was on developing libraries. As I said before, we didn't have a very powerful trigonometric library. As a matter of fact, we added several axioms for the trigonometric functions and arctangent. I added them. It was my fault. I added the actions for atan, and like 4 of those actions were wrong. I mean, I gave the wrong sign to atan because atan is a little bit complicated with the. I mean, not complicated, but you have to be careful with the signs x and y. So I in some of the quadrants I was giving the wrong sign in the axiom. Fortunately for the kind of problems that we were solving, we only focus on one particular quadrant, and we didn't use those axioms. But it is very easy to introduce inconsistencies even in well-known theories, and we decided to spend a lot more time on developing libraries and foundational libraries. So now we have a foundational library for trigonometric functions. And indeed, we develop and we have maintained for more than 30 years the NASA PBS library. Currently, it has 53 developments and more than 30K formulas. And we have fundamental developments, real libraries, logarithms, etc. But we also have more structures, for example, the series, graph, vectors, matrices, interval arithmetic, some libraries for reasoning on programming languages like while, small while programming language, and lately PBS0. I'm going to talk about PBS0 a little bit more in this talk, and some applications like term rewriting and applications to aviation and fault tolerance. There are more specific applications. They are not released as part of the NASA libraries because of the the process for those specific applications, for releasing those is more complicated because those are not considered fundamental theories. However, they are at the end, they are released, and the take and avoid libraries, for example, they are released now on their open source on license by NASA. The libraries are not static in time, and something that is happening is that those libraries are evolving from formalization of mathematics to more algorithmic verification. As an example, for example, graphs, they were developed very, very early in the history of the formal methods group, but it was the whole graph library was developed as a formalization exercise where we didn't have applications at that time. That library was developed before I joined Langley, so it was in the 90s. Many interesting theorems. However, when we start to have applications for graphs in our applications, in our domain, the library was not that useful. For example, vertices, edges, they were represented in sets, and the problem with sets is that they are good for formalizing and proving properties, but they are not as good for when you want to write algorithms with them, and then when you want to evaluate those algorithms, ground evaluate them, and to animate them. So there has been an effort on converting those libraries into more the libraries that are more useful for applications. So changing the data structures from something that is easy to verify to something that is more useful in implementation of algorithms and verification of algorithms. And how to do that in a way that we don't have to redo the whole library. So we invest some time and research on how to move and how to transition libraries, in particular how to do refinement of types in libraries so that they are more constructive. The library is not only about development, it's also about scripts, for example, for batch proving, for dependency graph, for animation, for differential testing. That is something that we have invested a lot lately. And differential testing is we have these models that are specified as PBS functions, and we have implementations also, and then we can run test cases in the implementation and in the PBS functional specification, and then we can check the results. So we have some scripts and tools for doing that in PBS. Something that is becoming a problem, an issue is library management, and this is something more recent. So we need to keep track of versioning, for example, so that the developments depend on particular version of the library, because libraries evolve, and then we have to be careful when we have a development that is not going to break because the version changes. We haven't solved the problem, but I wanted to mention this because we have to do proof engineering. I mean, not only how to do proof, but how to maintain those proof and how to maintain those dependencies. And this is not only a problem for PBS. I imagine that it's a problem for other term proofs. Very proud that the PBS library was featured in a movie in The Martian. the PBS library plays a role. I mean, not that important, but it's nice to see these kind of developments in the entertainment industry. So let me move to other things like strategies, for example, that we develop in order to do verification on numerical systems. At the beginning, we added low-level strategies for algebraic manipulations, and something that I call X strategies, that are the missing strategies in PBS. But then we move into more sophisticated strategies, producing decision procedures, for example, and sound numerical approximation. So it is good to have something like multitasking, but at some point you need actual verification, proof-producing verification and sound for some property that we are trying to prove, and we have developed several strategies for doing that. Not only strategies for proving, but also tacticals. So we spent time on this is more proof engineering, how to write good tactics, and this may be a little bit specific to PBS, but things like how to manage labels, how to manage names, strategies that introduce new names, for example, Frisch names and Frisch labels, and a particular scope when these names and labels can be released. So we develop these kind of strategies in PBS. So now let move to the title of my presentation. It is about embedding. So now I'm slowly going into that direction, and let me start with what I call high-level structure. So again, everything started with AILS, with the verification that I talked at the beginning of my talk, and this is a particular formula that we have to verify in PBS. It is related to the maximum angle. What is this? I forgot. I mean, phi is the bank angle. V is the ground speed of the aircraft, and I think that this is a computation related to the turn rate of that particular aircraft. Anyway, we have to prove this formally in order to finish our verification, and the way that we did this proof at that time, we introduced some lower and upper bounds approximation for the trigonometric functions, and then that lower and upper approximation, they have an iteration, and then we increase that iteration, that we get a better approximation, and at the limit we get the value. So that was a good way to prove this kind of properties. However, when we did the proof, all this was done by hand. I mean, the lemmas, these formulas that you see here, they are lemmas that we use in order to verify this particular property. And then for every function that we needed an approximation, we have to define these lemmas, and we have to use them. So it was a good approach, but it was very manual. We decided then to do that in a more mechanical way, and then we started with a formalization of the interval arithmetic. So these are the standard definitions of interval arithmetic, and then we have for this interval arithmetic, we have the proof that the inclusion property. And then we define strategies in PBS that use this interval arithmetic in order to prove properties like the one that you see there. So these are the kind of structures that we introduced at the beginning. I mean, more domain-specific structures and something that allows us to write the strategies. But then we move, can we do better? I mean, can we have a higher level of structures? And then I'm talking about embeddings. And what is an embedding? And so you probably know an embedding is a semantic encoding of a formal language into another one. And in this case, the language that we are encoding, I call that the object language, and the target language is the proof assistant. And what is special about embeddings? I mean, it's a formalization, but what is special about this formalization is that, in general, when we are talking about embeddings, there is a semantic function, there is a notion of an environment, and there is a notion of variables. I mean, variables in the object language. So we need to interpret those variables in a particular environment, and then we have some deductive properties. And for the case of interval arithmetic, then we move into an embedding. So we need to talk about interval expressions. I mean, not only the intervals as objects, but the expressions, interval expressions. So we develop a deep embedding of interval expressions in PBS. And this is the definition. I mean, it's a inductive data type, and then it's a deep embedding because we are talking about the object is a data type that we can quantify and we can enumerate. So an interval expression can be a variable. It can have an addition, an abstraction, negation, absolute value, negative, etc. And more complicated expression. And then we also need a type for the environment. And in this case, that environment, so these variables that are the interval variables, the ones that you see in bar IDX, are going to be interpreted in a box, and a box is a list of intervals. So the variable 1, for example, is the variable 0 is the 0 element of the list. And then in order to have an embedding, we need to evaluate and to have a semantic relation, and we need to define two functions. One that is the evaluation for real numbers. So how to evaluate? What is the meaning of evaluating this expression with a particular number for every variable, and that it should return a real number. But then we also need, and this is a recursive function. I'm not going to the details, but it's just a recursive function on the real expression that we are evaluating. And then we need a second evaluation, that is the evaluation for intervals. So in this case, the same real expression is going to be evaluated, but it's going to be evaluated in a box, and it's going to return an interval, and is defined using a recursive function. And then with these two evaluation functions, then we can define now two theorems. One that is called the inclusion theorem, that is like the one that I presented before. If the expression is well typed, then the evaluation in real numbers is included in the evaluation in the interval arithmetic setting. What is important here is that this theorem is fully proven in PBS, because everything that you see here is available in PBS. So the notion of well type is a notion of well type that needs to be defined in PBS, and for these data types, the evaluation is an evaluation in PBS. So it's a function. Eval is a function that can be evaluated in PBS, and eval for interval is also evaluated in PBS. So this is fully formalizable in PBS. And then the other theorem, that is the fundamental theorem, says that we can, if you are familiar with interval arithmetic, you know that one of the problems is the dependency problem, that a variable appears twice, then you lose precision in the interval arithmetic. But a way to deal with that problem is to subdivide the interval, so that you take the whole interval, divide that in two, and then the precision for the smaller interval is going to be better. And these fundamental theorems guarantee that this is the case. If you have a box that is including another box, then the evaluation of one is including the other one. So this is the one. This fundamental theorem is the one that allows for subdividing intervals. And again, this theorem is proven in PBS. So the big jump that we did at this point was now that we have this structure, now that we have this embedding, we can implement strategies by computational reflection, so that that we can use the development in PBS in order to write the strategies. And I'm getting late, so let me go into structural embeddings. That is the title of my talk. So what is the status now? The verification of air traffic management is routine now, but formal methods are still far from the practice in engineering. And so no, we need to get into specifications that are closer to the problems that we are dealing with. And then I want to go very, very back in my career to a paper that I wrote with John Rushby when I was a postdoc at SRI, that was called Structural Embeddings. And the idea of structural embeddings is, let's use embeddings that are deep for the structural elements of a language, but are weak and shallow for the basic expression, meaning that we are combining the structure of a method with the intrinsic elements and the primitive elements of the proof assistant. And this way we can provide methodological elements to a theorem prover by using these embeddings. So one of the embeddings that we did at the time was called PBS, that it was the B method in PBS, where all the abstract machine refinements and implementations are those of B, but then internally the basic structure of, for example, the set theory is not the set theory of B, is the set theory of PBS. So it was mixing the semantics of the B method, the semantic of the structure, and of B with the semantics of the set theory in PBS. And so we implemented that. It was we haven't used PBS for several reasons, but I think that now we are getting to a point where we can use this kind of embeddings. So to mention a few of the problems that we had in 1989 when we tried to do this deep embedding, is that we didn't have libraries, we didn't have good strategies for dealing with the set theory in PBS, for example, and then we didn't have good syntactic tools so that we can write like in B, but internally is represented in B. So let me skip this structural embedding of PBS in PBS. It's a little bit technical. Let me talk about some of the more recent structural embeddings that we have in PBS, and there is one on differential dynamic logic in PBS. So we have a deep embedding of hybrid programs. We have the assignments, the differential equations, the union, and this is the logic using the Chimera programming verification system. This is for proving properties about hybrid systems. So we implemented this embedding, but internally, so all the differential equation, all the structure, all the hybrid programs are coming from DDL and Chimera, but the primitive functions that are in the embedding are those of PBS, are real numbers in PBS, are real functions in PBS. The substitution, for example, that is one of the, you read the papers about the DDL, the substitution operation is quite important in the semantics of DDL. Well, that substitution in PBS is implemented by beta reduction using higher order abstract syntax. Then we also implemented the dynamic DDL rules, the DDL rules as proof strategies in PBS. So with this embedding, you practically can have reproduce a proof in Chimera by using proof strategies in PBS, by using the whole PBS. So what is the advantage, and why do we want to do that? Because we want to provide a way to do verification of hybrid program directly in PBS, a la Chimera, where it's a higher, it's closer to the kind of programming languages used by engineers. But you have all the infrastructure provided by PBS in these embeddings. I don't think that this is published yet, but this is we have a couple of talks on this embedding. There are a lot more embeddings in PBS. We have floating point programs with conditionals and loop. We have in this CPP structural natural language for requirements, and that is embedded in PBS. So all these embeddings are coming. Let me say something, and is that I think that we are in the golden age of embedding. So it's not only in PBS, but absolutely everywhere I see there are embeddings and in programming, in verification systems, and this is a very good direction in my opinion. Why we are in the golden age of embeddings? Because the specification language that we use in proof assistant, they are very expressive, because now we have the extensive library that we didn't have before, because now we have improved automation that we can use in these embeddings in order to take advantage of that. Because we have now IDEs that are extensible and are advanced, and we can change the syntax, and we have dynamic syntax, for example, and we can use all these features in order to mimic new constructs, syntactical constructs, not only in the input but also in the pre-printing. So this is the time of doing embeddings, because we have all these nice utilities in theorem provers to do that. And there are plenty of applications, specific domain applications where we can use the embeddings, like requirements, like data change formats, for example, like architectural description kind of languages, safety cases. Okay, let me finish with a sentence that I concluded in the paper, and it's what was our recommendation at the time, and it was to structure theorem provers in a way that is easy to work with these embeddings, and I wanted to check how we are doing in PBS, and this is what we have now in PBS. In the PBS, we have the composite in several APIs and use them in different embeddings. So let me finish here. I'm sorry, I took a lot of time talking about this story and not that much on the subject I wanted to talk. This is the end of my presentation, Laura. Thank you. Sorry.
Thank you, Cesar, for this nice presentation. So yeah, let's thank the author. And I don't know if there are any questions in Philadelphia first.
Any questions here? We have a couple. So you talked a lot about very interesting work in the real numbers, and there was only a very brief mention of floating point on the very last slide. Can you say more about how you integrate floating point approximation into all the other numerical bounds you're proving?
Yes, we have an embedding of. Thank you for the question. We have an embedding of floating point programs, simple floating point programs with assignments, bounded loops, and function calls. And it is used, that particular embedding is used to compute a round of errors. And we have developed a tool that is called Cesar that is able to compute this round of errors based on this embedding and produce proof certificates for the programs where we can check that the round of errors computed are correct. It is integrated with Framacy, for example, so there is a whole tool chain on how to do this. And we have used it to prove, for example, the correctness of some air traffic management kind of problems that are written in C, in Framacy, and then with this tool chain, we can prove the correctness of the program in PBS and in conjunction with the Framacy tool. We have a couple of papers on that if you are interested. We can talk offline. But this is more than embedding. I mean, there is a whole tool chain that we have developed in order to do this verification.
Thanks. We have one more here. Hi, thanks for the talk. And so I have a related question on the interval, the one based on the intervals. So have you considered imposing some kind of conversion rate on the sequence of the intervals? Because I don't think that was part of the definition.
No, we did not. But we move into other area with the interval arithmetic. We move into the area of rigorous polynomial approximations. So, I mean, interval arithmetic is one of the enclosure methods, but then there are other enclosure methods like fine arithmetic and Bayesian polynomials. So we move into generalizing these strategies to work with an arbitrary enclosure method, and we define a branch and bound algorithm that is generic for the enclosure method. So at the end, we have a strategy that is generic with respect to the enclosure method, and we can instantiate that particular strategy in PBS with different enclosure methods. So some of those enclosure methods have better approximation behavior. So we didn't move into the rate of convergence, but we move into generalizing this idea to other type of approximation.
Thanks. There is a question by Andrei that he wants to say. Andrei?
Yes, can I speak? Yeah. Hi. So this concept of structural embedding seems really interesting and fruitful, and indeed, I think it can lead to some really productive work. But let me play the devil's advocate here. Don't you need to be careful with the properties that you verify for fear you may have too many behaviors? You may have, let's say, false alarms in terms of the proof not working because your basic actions are too expressive. Are there any problems on this front in the sense that you need to clearly delimit the properties that you are verifying?
Yeah, that is true. I mean, I think that structural embeddings are good when you don't want to be semantically equivalent to a particular method, but you want to have something that is very idiosyncratic with respect to the proof system that you are using. So, for example, in the case of DDL, I mean, the fact that we are using PBS expression and real numbers, and even the logic in the embedding means that we can have the dependent types of PBS in these DDL programs that was not original. I mean, typing dependent types is not original in the semantic of DDL. So we can have those elements kind of for free in the embedding. We can also talk about some functions, arbitrary functions that are not the ones in the DDL logic, and conditionals or lettings, for example, that are not defined. However, there is nothing is free, and the problem there is that by adding those elements, things may not be automatic as you expect. Somehow you have to be careful that the strategies or that the logic is still consistent, and that you are not showing more than that you can, that maybe something that was decidable before and now it suddenly is undecidable, and then is not useful anymore. Yeah. So yes, I mean, it's very tempting to do the structural embeddings and get the freedom and everything that is for free. But then you have to be careful with all the complexity that you are adding. I mean, you may be adding more than you want.
So if I can have a quick follow-up. So it looks like when you are embedding a logic in PVS, if you get more expressive, yeah, there's not a bad problem to have. You have to work on the automation. And I think you mentioned that you would verify things directly in PVS in Chimera style, let's say. So which is really nice. But when we are talking about embedding of programming languages or of the actual systems specifications in PVS, then you may have some additional behaviors in the system.
Exactly. It's like, I mean, I have a good example. I didn't have time to talk about that, but we embedded first order functions in PVS. So that we call that PVS 0. That is an embedding of PVS in PVS. And then you get very strange things. I mean, it's not. I mean, I don't have time to talk about that, but you have to be very careful about what you get, because you get more than you wanted.
Yeah, thank you. Very interesting. Thank you.
So I guess we don't have time for more questions, but maybe you can write to Cesar if you have more questions for him. And let's thank the speaker again, and thank you.
Thank you.